I'll start the recording. So the last time, as you may remember, we have taken a look on how variables are represented within a computer. So to quickly summarize it, we have the machine types, which the CPU can operate with using individual opcodes, and those are 1 to 4 or 8 bytes in size. They can be signed or unsigned. Signed means they can be positive or negative, or unsigned meaning they are 0 or positive. And we also mentioned that for floating point numbers, there is a separate set of registers, and those numbers are treated separately, so there are individual different opcodes used to work with those numbers, as well as they are special instructions used to convert from floating point numbers to integer numbers and vice versa. So this was further down here, as it was here demonstrated with this small piece of code. And today we will take a look on pointers. So we will create a new project. We have already mentioned slightly pointers in the last lecture with regard to the size t and UNPTR pointer types, which we will now take a closer look on. So let's call the project pointers. Let's make this bigger. Okay. Zack. Let's remove the things that we don't need. So, as it was already mentioned also in the last lecture, pointers. As was mentioned in the last lecture, all the variables which we usually use in our program live somewhere in the computer's memory, and usually those variables are assigned memory locations. So as you definitely know, a computer has a certain amount of random access memory, which is used to store temporary data during its operation. And this memory space can be addressed by an offset. So it starts at 0 and goes up to the highest value that the pointer on a given architecture supports. On a 32-bit system, this is about 4 billion. On a 64-bit system, that is 2 to the power of 64, which I don't know how that number is called. Something exabyte or something like that, probably. I think it's 16 exabyte. We can quickly check that. Probably will be exa, but let's see. So an exabyte would be 10 to 18, and if we take 22 to the power of 64, we get 6 times 3, that's 18. Yeah, so that's it is well, here it's 18, but in the steps for memory notation you usually use powers of 2, so you don't go with steps by 1000, but in steps by 1024. So the numbers, if you use the suffix x, are a bit smaller, so it will be 16 exabyte that you can in principle address. And since our variables are somewhere located in this address space, C and C++ give us the ability to address those variables not just by name somewhere within our program and leave it to the compiler to find them, but we can actually address them directly by the offset. So let's define a variable for testing. Int myVar, give it a value. So if we just put a very simple breakpoint here and run this application, we will be able to see where its memory location is. So here we have our variable, and in locals we see the value of the variable, and in the imnet window, or actually also here, if we that should be all enabled. Yeah, we see here. What does it do? So it copies to Mava. We need to address. It only shows us the name. That is not great. It should show us also the position. But we can, for example, write the end sign and then the name of the variable, and then we get the address here in this imnet window. Usually show addresses. Okay, so if we turn off show symbolic names, it will show us also how we can get to the address. So in this case, you see this that it uses the register RBP +4, which, if we evaluate, will also give us the exact. It's not in hex. Let's enable hex display. It will give us the exact same number. So, as you already see, the addressing, how it happens within a function body is that the memory addresses that are used for variables are usually relative to a value stored in a register. In this case, this is the base pointer register is used. The R, as we mentioned last time, denotes that it's to be treated as a 64-bit register. If it would be E, then it would be used as a 32-bit register, which in this particular context would make no sense. But when the extension from 32-bit to 64-bit was introduced, you got for all the registers the E notation to be available just in case. So now, of course, the initial value of this register will be determined when the stack for the thread will be allocated. So when you create a new thread in a modern Windows operating system, a certain amount of memory is reserved for this thread. It is called the thread stack, and the initial memory location of this thread stack will be saved in one of the registers, and then when the stack, when the thread's execution starts, the registers like RBP and RSP will be filled with values which denote the current position in the stack. When you enter a new function, those values will change. Also, the use of the RSP register is usually mandatory. The use of the RBP register is optional. In the debug build, these registers are both used. In release build, you can enable a flag to not use the RBP register, in which case here the opcodes would just reference the RSP register with an offset similar to here. The idea is that when a function call starts, then the top of the address space, which is used by the function, will be saved in the stack pointer register, and then in the RBP register, and then in the RSP register, as new data are added, the next free address will be kept track of, so that when within a function new memory is needed, it is quite simple to get the next free memory address just by taking the RSP register that already points to the free address. You can then choose if you want to use 8 bytes, 16 bytes, 24 or whatever amount suits you, and then you will just increment this register by this value for subsequent opcodes to use. And of course, you would then want to put the RSP plus whatever the current old RSP value into some register, like here the RBP, that you can then reference. So what in this very simple function at this level happens when we go from the start, we have this push instruction. What it does is it will take the value of the RBP register, it will write the value to the address pointed by the RSP register, and it will automatically increment the RSP, or rather decrement the RSP register by 8 bytes. So this is a interesting implementation artifact of the stack as it is used in x86 and many other CPU architectures. Unlike what would be intuitive, where you start at 0 and then grow your use memory space towards 1, 2, 3, 4, 5, etc., etc., towards positive numbers. The stack starts at a given value and then grows downwards. So the advantage of such an approach is that if you are, for example, programming for a microcontroller which just have one thread and doesn't do anything highly complicated, then the compiler can just allocate the memory that you need statically on the top of the address space, and the stack will grow from the bottom of the address space as your function calls are calling other functions, etc., and recursively invoking other functions. So as said, we pushed this value, then we also save the value of the RDI register. Then we add some additions, we reserve some space on the stack. This is here done because there is a function call to this just my code function, so we could quickly disable this and then view how our code will look when it's slightly cleaner. So we go to those, I think, in the general option, yeah, here, just my code debugging. No. Then we can just recompile it. And now we see that the function is already much simpler. Since we don't longer need to make a function call, function calls will be explained in a later lecture, so don't worry. Everything will come in time. Here, in the simplest case, again, we save the old RBP value. The reason why we need to save it is, as I explained in the last lecture already, some of the registers are defined as volatile, so that if you call a function, after the function call, all the values of the registers might be changed. And some other registers are defined as non-volatile, meaning if you call a function, the function can do its stuff, but it's responsible for restoring the original value of those non-volatile registers. And the RBP register is one of those non-volatile registers which needs to be restored if we exit, which will happen further down in this code. So again, we save those two registers. We create some space on the stack. In this case, that is quite a bit more than what we need, but why not? It's a debug build, so having more space is fine. We can in fact take a look into the address, since RSP will, as far as I see, no longer be modified. So we can take the address of RSP and then go to our memory location and go there. And then here it starts, but I said it starts in that direction, so it would go upstairs, and at some point we would have our 1, 2, 3. We can, for example, here also put something more easy to spot. Let's go with 1, 1, 2, 2, 3, 4, 4, 5, 5. Wait, that was one too much. That should be enough. Another interesting thing that you might notice is that now the address which we have from before is no longer valid. This is because when the program restarts, it will of course allocate new memory areas and usually get new addresses. So you cannot rely on these values to stand change. And we see here that that in this position of the memory, our variable effectively lives. So, as said, we reserve some additional memory. Then we move the content of RSP to RBP. Since we saved RBP, we are free to modify it. And then now here we have the instruction which fills our variable. So this is the same as last time. It is a simple move instruction. If we would be in a different architecture, like an ARM architecture, that would already require 2 operations here. Also, using a value like 1, 2, 3, 4, 5, which is a 32-bit number, would require to load the value from another position in the code. But I think since we only have a limited time, we will mostly focus here on x86 architecture, since ARM is something quite novel, and unless you intend to program for Raspberry Pi, so you will not experience that much. So for programming some software for lab PCs, in principle you will also not need to program anything in assembler. This is really just for the understanding. So we will focus on the C part of the programming experience, but it is good to have to develop certain internal mind models of how those things are represented inside the computer to this helps you to avoid various issues and bugs which can easily be done when programming in C++. Okay, so as said, here we write the value to the memory location, which, as we said, is just RBP plus an offset. And then what we here, our function already ends, but there is some function epilogue. First of all, we clear the AX register, or the RAX register, that's effectively the same, to be 0, since the function would expect a return value. So normally we should have right here return 0, but for the main function, the compiler does this for us if we forget it. For other functions, it will produce a warning. Then we can restore RSP, the value of RSP from RBP. We can then use the pop instruction, which will, now that RSP has been restored, read a, so it will decrement RSP and read a 8-byte long word from it and save it to register, and then to repeat the same thing for the RBP register, thus leaving the non-volatile registers in the same state as the function encountered them. And finally, it will return from the function call to the location in the code from where the function was called. So a pointer is something that we can use in our code, which effectively is just a integer value, well, a 64-bit integer variable in our case, which can hold some value. As we already have seen, the actual memory addresses each time you restart the application will change, so you cannot use static addressing here. What you can do, of course, is you can assign certain known, let's call it magic values. So a magic value is something that indicates something and can easily be distinguished from actual valid values. So the typical magic values which can be used with pointers are 0, since the way now 0 is a quite peculiar magic value, because hypothetically 0 would be a valid memory address, but the way Windows operates is that it would never allocate to an application a memory page starting at 0. So effectively this address will never be valid within your program, so you can use the value 0 to indicate that your pointer, for example, does not hold a value yet, or that it holds an invalid value, depending on the semantics of your application. Another value which you can also use for pointers to indicate that they are invalid or uninitialized or etc. is -1, although here you need to use a typecast to make the compiler accept the -1. By default it only accepts 0, or you can use the null preprocessor macro, but it's just a preprocessor macro, so if you go to it in the C runtime, you will see that it is just defined as null. It is not a real keyword, it is just a placeholder that gets replaced. We should include probably something. So that we have our null defined. And this much to this. So if we now run the code, you will see that this pointer will be filled in a very similar way. The only difference is that it will use a different addressing. So it will say that it's a Q word, so a quad word. It has 64-bit, even though we are just passing the value 0 to it. And also when we show the actual code bytes, you see that here we are using a different opcode as before. So the 48 prefix for the regular move opcode indicates that this is a 64-bit operation. This 48 is used quite often with various opcodes that can take 64-bit registers or addresses. So if you don't have a disassembler at your disposal, it also helps you to spot those types of instructions. But for now, this of course is not so important. One thing that we can also do in C is we can so let us so we can make the compiler tell us the size of a certain type. So we can write, for example, int test var is equal, oops, it's not typing, sorry, int test var is equals size of. So the size of keyword allows us to determine the actual physical size of a variable. So in this case we'll do it with our variable and our pointer. Test KTR, and if you run it this time, we will not first of all, the compiler is quite efficient about it, so it just assigns static values. It just replaces it with a static value. But using the variable proof, you can see that our integer is 4 byte large, but our pointer is 8 bytes large. And if we switch here to a 32-bit platform and then compile again and run it, we will see that the pointers will be reduced in size. Okay, it needs a second to load a few things. The pointers will be reduced in size to be the same size as the normal integer. I think I mentioned this already last time, but it's good to have here. So as we said, we cannot use static values except for indication that the value is not yet initialized or like. So how do we get a an address of a variable? Very simply, we use the AND operator and prefix a variable name with it. So here the compiler will give us the memory location of the variable instead of the content of the variable. And when we have the pointer, now if you would assign to the pointer something, let's say int 1 2 3, you will see that doing so will not change the value of our variable. This operation will change the value of our pointer. If we disable hex view, we see that it okay, it always shows pointers as hex. But if we disable this and cast that here to an integer, the 64-bit integer, of course, you see that the value changed, but here our original value of our variable remained unchanged. So if you go back to the hex, we see that it still is 11223344. This is because a pointer is nothing else than a normal large enough integer type variable, and it just holds a memory address. The only thing that makes it special is how we treat it, how the compiler interprets the meaning of this pointer. It is not an own machine type or anything. It is just an integer of sufficient size to hold memory addresses. So if we would want to change the value of my variable, how would we do it? We can do it with the dereferentiation operator. When we prefix a pointer with an asterisk, this tells the compiler that we don't want to change or read the pointer value, but that we want to read or write the value of the memory the pointer is pointing to. So now, when we run the code this way, we will see that the myvar variable will be changed. As you see now, it's 7b, which corresponds to 123 decimal, while our pointer is still pointing to the same memory address. So if we put the breakpoint 1 point earlier and run the code, you see that that's our pointer and that's our variable. You see also that it often with pointer shows in brackets the value the pointer is pointing to if the type is known. And if we make the step and then repeat our interrogation of the values, we see that the pointer stayed unchanged, but the memory it points to at myvar has been changed. In C and C++, pointers are a extremely important part of the programming language. They allow you to do a lot of things that otherwise would not be possible. And they are also, unfortunately, the biggest source of major programming mistakes. So typical programming mistakes with pointers can be that you try to write to a pointer which has an invalid value. The value can be invalid either because the pointer was not initialized, or because the pointer pointed to a memory address which then has been reused for something else, and by writing to this memory you will write effectively garbage to a random location within your application. So this is really, really bad, and you should try to avoid such mistakes as good as possible. And one way of avoiding those mistakes is to use so-called smart pointers. This is something which we will take a look into much later during the lecture. The important thing to know about smart pointers is that they are only available in C++. Normal C is not object oriented and has no concept of such mechanisms. So here, let's continue our pointer examples. So here we have assigned a value to the to our variable. What we also of course can do is we can create a new pointer, pointer2, and assign it the value of our initial pointer. And then if we then access this pointer, then let's say 5, this value, then we'll again just change the value of our variables. No matter how many pointers you create to a given memory location or to a given variable, in this particular case, I forgot to put the breakpoint here. Without the breakpoint it doesn't break, obviously. But here again, first thing we can see is that both pointers hold the same value, although they themselves live in different memory locations. So we can do the same thing as with a variable. We can get a pointer on a pointer, and then a pointer on our other pointer, and here you see that the pointers live at different locations, point at the same memory, which has the same value. And if we change it, again here it changed now from, I think it was C, I don't remember, 7b, and now it is 1c8, which is just text representation of our other number. So pointers are really extremely powerful because they allow you to give a arbitrary large amount or block of memory to some function which can do something with it, and the values will be written directly to the memory that you have gave to the function. It does not require you to copy the data when you are making function calls or returning from them. And what you of course also can do is you can create a pointer on a pointer. So you can have a point, and there is no limit how many pointers on pointers on pointers on pointers on pointers you can have. So in this case we have a that needs to be 3. We have a pointer on a pointer, and if you would want to change the original value, we need to use 2 asterisks. If we would use just 1 asterisk, then we would change the value of pointer2, which would be a mistake because then it would contain an invalid value. So now when we go here to our initial variable, it's again a different value, and when we look in decimal we see it again assigned the value, even though now it went like through a couple layers of, let's say, misdirection. Again, as long as the type is known by the compiler, the embedded window here will dereference the values for you. So you get the address of the value of the first pointer, which holds the address of the second pointer, which holds the address of the variable, which holds the value which we just written to it. So for example, what you could do, what would be a bug, would be if you would have only one dereferentiation and then try to use this pointer. So in this case, the compiler, however, sees that, wait, this is a number. A number should not be assigned to a pointer, so it will not compile. If we try to run this, then we will get a compile error. Of course, we can force this to be done by it should be up. And if we run it, then here the application crashes because trying to access memory at the location 456 just tries to access a page which does not exist in memory, and this results in a write violation. So as said, pointers are dangerous but also very helpful, so just be careful what you do with them. And there is however in C++, not normal C, a way to use pointers implicitly. So the use here is an explicit use where you have really a variable which you can assign a number to, and it will really do whatever you tell it. Even if you tell it to do something dangerous, it will do it. You can, however, use so-called references, which is just as a kind of abstraction from a pointer. So instead of using the asterisk, you use the and symbol in your variable definition. My ref is equals. The differences are that you can, at least you should not be able to define just a reference. You see the compiler here already complains. The reference needs to be initialized with some address to a variable, although it abstracts this away from you. So we are initializing a reference in a way as you would a variable assignment. So if we again here make myvar2 and change myvar2, this is equals to, let's say, null. Then here we have a new variable which gets a copy of the variable 1. And now after this change, var2 is 0, var1 or var without a number remains what it was. Of course, if we put a breakpoint earlier, then we really see. Well, okay, actually that we don't see because it is. Oh no, sorry, we can put a breakpoint here. Before it executes this code, we see that this is 1, 2, 3, 4, and the other one as well. But as soon as we step through the operation, the one variable changed and the other variable did not, because the variables are copies of each other. They are not referencing each other or are not pointing on each other's memory. They are clones in the sense. But a reference like this here, internally you will see that the code of such a reference is the same as what we do here, for example. But semantically, you can interact with this reference variable the same way as you would have interacted with your original variable, and whatever you do to it will end up being written to your variable here. So let's go for some value that we can recognize. We have 2 breakpoints, we run it. So we had our variable, it was 1, 2, 3, 4. Here we had the pointer. The pointer we assigned the value to 3, 4. Then we had the pointer of the point. Then again here we changed it. Then we changed it again. So now our variable should have the value 7, 8, 9. Okay, we need to disable hex view, and it does. And now if we here execute this code, our variable will change its value. Okay, we need to re-enable hex view such that we can recognize it to the ABCD value. And if we go back to our disassembly view, you see that here the assignment operation is done as follows. First, we get the address into the rex register here. So we load the address by adding the known offset. So then the values which are used here are determined by the compiler during compile time. So the compiler, when it builds the function, knows where it allocated each variables, and then it knows which values needs to be added to RBP to address each individual each individual variable. And if we scroll further up to our 1, 2, 3, you see that this is a sorry, where was it here? That this is pretty much the same operation. We have rex field with the address, and then read the reference rex and write a value to it. The same what happened here. Now the representation is slightly different because here it added zeros, but it doesn't really matter. Without zeros, it's still valid. So this sort of abstraction gives you the safety, usually, that the variable which you are using will always exist. So if you add some scope, then you can of course use variables which are outside of the scope. If it would have a scope here, you cannot try to access any of those variables, or you cannot try to access any of those pointers. What you could do if you want to manufacture a bug is you can define your pointer outside of the scope, and then I try to write to the pointer. Let's see, 0. Now this operation is invalid, although probably it will succeed because it's a write operation to a memory block which previously was used, so it is allocated. And if you write to it 0, it will do it, but it's basically a nonsensical operation because this memory will later be reused for whatever else your program will later do. So you shouldn't do it. Of course, you could also try to read the value from it. You could make a new variable int test is equals this. This will give you something. In certain cases, it might give you a valid number. We can run it just to see how much it will misbehave. Of course, if we would not initialize the pointer at all, it would just give us a dereferentiation. As you see here, the last value that was in this memory region still is there, so the compiler did not clear this for us, even in the debug build. It normally only clears memory on function initialization and exit, since it wants at least to maintain some level of performance. Clearing all the memory on every scope close would be too much unnecessary work. Although it would of course help you to find such a mistake, because if it would have cleared the memory, it would then fill it with DDDDD value. So you would be able to spot it at the first glance this way, even though semantically this sort of code is invalid. It looks correct, it does what you want it to do, and it might even work for years without any issues, and only fail in some very special edge cases. So let's quickly undo this change that we did. And as said, this sort of mistake cannot happen when you are using a reference, because any assignment to this reference will actually assign the value to the memory address you are pointing to, and not change the reference itself, even though under the hood such a reference and the pointer effectively do the same thing. So the next thing where pointers are crucial in C and C++ are arrays. So an array of elements, I guess you know from mathematics, can be, for example, a vector where you just have a certain amount of variables of the same type. And of course, if you would just write variables like int var1, 2, 3, 4, 5, and so on, 1, 2, 3, 4, 5. You could reference them individually, but you could not have the program determine in runtime which of those variables it wants to reference. Or rather, you could, using a very complex contraption of if and else statements, but that would not be a good practice. So what you do instead is you define a so-called array, which is in memory pretty much the same thing as just a few variables one after the other, but the semantics of the array allows you to address them by index. So my array, let's give it 10 elements. So oops, there should be an A and not AR, my array. And the array can be defined in two ways. So you can either define it like this, or you can assign, well, actually in three ways. You can assign initial values. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Now, if you would assign only values up to 6, the compiler would normally fill out the rest with zeros. So you can, if you want to initialize an array all with zeros, just write something like this, and it will effectively just fill the memory with zeros for you. But if you have the amount of elements you want, you actually don't need to say to the compiler how big the array should be. So you can define an array like this, and then the compiler will say, okay, how many initializations value we have? Okay, we have 10, so it will be a 10. If we would have 0, then it would assume it's just a single variable effectively. But for completeness, let's go with the full way of initializing it, which, as said, in this case is slightly redundant. But of course, if you would want to only initialize everything with zeros, then you would need this, because then the compiler sees, okay, it should be 10 elements, we only have values for the first one, then let's fill everything else with zeros. Suck. Okay. And now let's do a simple example how such an array can be used. So we will later take a closer look on flow control. So here for now we will only use a loop and just assume that we know what we are doing. And later we will then take a look into, so in a later lecture, how this flow control and how such loops really internally operate. But for this example, it is quite useful to have it. So A typical loop in C is a for loop. It takes a initialization instruction. So for example, int I is equal 0. So we can initialize a value or multiple values. Then it has a condition. So the condition specifies, so as long as the condition evaluates to true, the loop will continue operating. So for example, we want I, so our initialized index to be smaller than then effectively we want it to be smaller than 10. So let's first start with a simple way. We just write smaller than 10, and then we can use the plus operator in the third part of our for loop. This part is executed whenever the loop's body is finished. So the loop has a body, and during the first run of the loop, the initialization is done. Then the check is done. If the check is true, then the body is executed, and if the body is done with the execution, this part is executed, and then everything repeats again at checking the condition until the condition is false, at which point the loop terminates. So here, for example, we can reuse our variable. We first set it to 0. And we can, for example, add to our variable using the plus equals operator the current value of my array at the index I. And now if we look into our variable, it accumulated the value, so that looks plausible. We could count it by hand, but we are too lazy for that. And one thing that one can, of course, optimize here is we would like the compiler to pick 10 for us, because let's say we want to later change it to 16. Why not? Let's start it at 0 maybe. Null xa, null xp, null xc, comma null xd, comma null x, null xe, comma null xf. I think that's, oops, that should be all. And then 10 would not longer be what we want. Or technically, this, of course, this would run because it's less values. If we would change it to 8, then it would be really bad, because then we would access memory which is no longer valid. We would access the 9th and 10th element, which do not exist. Oh, and one more thing that is important to note with regard to C and C++, that in this language the index in the array starts at 0. So the first element is 0. And in this particular case, if we go back to our 10 example, the highest element would be numbered with 9. So if you would try to access an element at the index 10, that would already be outside of our array's boundaries. And this is the case in almost any typical programming language. Some more, well, some less IT-oriented programming languages might start the indices at 1. Like I think MATLAB does that, because like people that do math expect indices to start at 1, so they did it this way. But for programming, start at 0 makes all the sense in the world. We will see why shortly. But first, we will try to find a way to fix this. So what we can do is we can use the size of command, well, keyword, and first get the size of the whole array. Now, size of array will give us not the count, but the total memory size of this array. The total memory size will be 16 times size of int, so 16 times 4 should be something like 64, which is not 16, so obviously we are not happy. So the cheapest fix is we say divide by 4. This gives us already the right value, and when we change the value here, it will always work, unless we change the type. If we change the type, then we would have a problem. So we can, of course, or if the compiler would change the type for us. So if we would run the code on the Arduino, the right value here would be a 2. So the first thing to fix it slightly is just use Caesar of int. That already takes care of this scenario where we change the platform completely, and then the compiler takes a different size for int, and then our code is invalid. So here it would remain valid. Although there is, if we would change in the code the int to something else, this would still be not the best option. The best option is to just take the 0th element from the array, and then no matter how we change the array definition, this loop will always only go through all the valid addresses, valid indices of the loop. So now the interesting thing is that while such a loop looks like a own type of variable, effectively it is just a block of memory and a clever use of pointers. So for most functions, wherever you can pass a pointer to, you could also pass an array value to. One thing to keep in mind is that this operation, so that size of a pointer would always be just the size of the pointer itself. It would not give you the size of the memory block the pointer is pointing to, and this can be a source of mistakes as well. So you can use size of array only if you know that you are using an actual array and not some sort of pointer. So here, let's try now doing the same thing the loop does here, but this time using pointers. So we reset our help variable, and we make an integer pointer, my ptr. Let's go with small r, and then we can just assign the array to our the array variable to our pointer. This is valid. We don't need to make like so this would be this equivalent, but we don't need to do this since the compiler knows that this is an array. It will automatically just give us the address in memory where this array lives. And now we want to make a loop that would do the same thing. So there are in fact two ways how we can do it with pointers. The first way is the simpler one. We just copy our loop from here. We close the loop, and here we write a slightly different code. My var plus equals, and now we take the address which we have in our variable. We add to it I, and then oops. So this operation gives us already the address. The important thing about the plus and other operators when operating on pointers, they do not operate in the increment of 1, but they operate in the increment of whichever type the pointer points to. So +1 will be actually +4 in this case, +2 would be +8, and etc. And of course we need to dereference this memory address. And then when we would run it, it would yield us the exact same result as we had before. We can write this in a more detailed way to demonstrate what actually happens here. So int asterisk my temp pointer is oops, let's use a small t, is equals my array pointer zack plus I times size of int. So of course I would need, of course this would not technically compile since it knows to use here the right increment, but this is kind of what happens under the hood in the code of the compiler. We cannot, if you would really run the code as is, it would end up in I being, it would effectively end up in this being executed. So this would not be what we want, but just for understanding how the code internally works, this is a good demonstration, and that's why I just write it as a comment. So this would be more or less the equivalent code. And the third way how we can implement the same functionality in our loop would be, again, first we reset of course our helper variable, and now we'll use a pointer. So my ptr, we already have defined it somewhere. We assigned our pointer to have the value of the address of the first array entry, and then we changed our check. So now our pointer needs to be less than our array plus 10, because it has 10 elements. We could also of course use plus yeah, we cannot. Effectively under the hood what happens is that it makes plus 10 times, like here, size of int. So the value internally will be corrected as we want it, and then to iterate to the next loop, what we'll do is just we'll use the plus plus operator to increment our pointer each time, in this case by 4, which would be again equivalent to writing my pointer plus equals size of int. Then of course we need to close the loop, and then within the loop we would just need oops, that was a mistake. We'll just take a line like this where we just dereference the pointer. In all these cases the result is the same. We are accessing our memory block at different offsets. So now let's put breakpoints in all the cases and compare them to each other, how they look in the assembler representation. Okay, so as you see here, first this is part of the loop. We don't care for the loop. The loops will be explained at a later point. We only care for this part of the code. So we fill our rex register with the address of R. Then we move to the EX register the rex, so the address, the value that is stored in the RBP register plus the value so these registers are the same, but they can reference each other because the value will be written only once the operation is completed. So we first have here our address, and then here we want to have the address on RBP. So here in rex is the value at the address at this memory location, and here now we want to add RBP, the value at this memory location, plus 4, times 4 plus these, and this is all this can be done. All the whole operation can be done with one opcode. So if we look on the bytecode, we see that it is actually not even that long. What happens here? In ARM, we could compile this for ARM later and run it if there is interest. Let me know if there is. Then this would actually require multiple individual instructions to do the same functionality. Okay, so we store this value in ARX or rex. So I said this effectively is the same thing. So we make a step here. We will have it loaded apparently 0. Then well, it's still loaded 0. Okay, well, yeah, because we are in the first iteration, so the offset will be of course 0. During the next iteration it will change. And here it will dereference and load the value. Well, it's also 0 because we've put 0 into our array. That is a boring example. Let's put something more interesting here. Let's start with ABC till F, and then have 0 at the end. That is a much more interesting example, or at least slightly more interesting. Okay, so again, the first, oops, they mentioned the last time, if you have the focus in the code and make the single step to just step over the whole set of instructions, you always need to click into the disassembly view to make a single step. So again, the first two operations will be still rather boring. No, actually this one already not. So here we already loaded the value, so A is 10 in decimal notation. So we already got our index, our value from the array. And the next thing we will do is here we will probably get the value from our variable. So ECX will be filled with 0. Yep. And now we add these two registers to each other, and the way the typical x86 instructions operate is that one of the operand registers is also the result register. In ARM it's usually different, where you have to really specify 3 registers, one to hold the result. So here we will change the value of ECX to be the sum of both, in this case just 10, since that ECX initially was 0, and now this is pretty useless, so the compiler could here just write copy the ECX directly, but for some reason they didn't do it. As said, the debug code is not optimized, so there might be unnecessary steps in those things internally. And then here we will be accessing the location of our variable my var and write a return value to it. And when we then go again through the loop, should I press? Okay, let's just repeat it. Having pressed at the right offset, it automatically brings you with the focus to the other tab. So we need to then click again here to have proper single stepping. So as you see, Rex is just our I variable. We can show symbol names that, well, for I it doesn't show it, but for the other variables it does. And then again it would perform the operation. And then if we remove the breakpoint and go to our other breakpoint, we will see that the code is quite similar. So again, we get our address, then we get our loop. Okay, it is slightly different with regard to the order of the operations, but for the most part, it just does the same. It gets our loop variable. It gets here our address. So when we step through it, first step this will be 0 because it's because I is 0. Then here cx that will be the address, the value of my pointer. Then here we will add so we can maybe quickly take a look what is within this variable. So if we say it's a int asterisk, you see that the address here, even though now the IntelliSense is just showing us a number, is still as before referring to the first entry in the array, which it will here take out of the array. Zack. Here it will now get the value, which will be 0 from my var, and then it will again do the addition, do the unnecessary move operation, and then save the result into the position of my var variable. So as you see, using arrays the normal way or the pointer way results in almost the same code. Is there a question? No question? Someone just sneezed. Okay. And now, of course, if we go further to our next example, it will be It will be different. So, since here a good part of the operation is already done within our loop body, the whole code with our loop increment stage here, you see that our loop body is actually simplified. So here again we get the variable, we get the address of our variable, then we get the value at the address, which is 10 as always. Then here we get the value of our addition variable and of our sum variable, and the rest is the same as it was before with the other implementations of the loop and of our variable array access. Okay, so the next thing we should take a look on what would be the next interesting thing? So we had already typecasting with regard to the yes, there is one thing that I showed you in the last lecture already with pointers, if you remember, the trick to get the integer, so to copy the value of a floating point number into a integer register. We can now maybe take a closer look on this again. Since now we have an understanding of how pointers work. So we will define some float my float. We will fill it with 123.45. Okay, that now we will first do the normal conversion. So int my int1 is equals just the float. So this just gives us the value, and then we will do our int asterisk my int ptr pointer, where we say, oops, it should be a int asterisk, and then take a reference on our my float. Zack. Okay, and now just for good measure, we will copy the value into a new variable. So my int2 is equals asterisk my int ptr. So when we run this, we will see again the behavior that here, when we just do the normal assignment of a normal variable not using pointers, it uses a special instruction to get the floating point number from a memory address and then save it to the EX register, which then is saved back to wherever our variable lives. While if we do it here with the pointer method, we will just get the address of our floating point number, but then just copy it as if it would be an integer. We will not do the necessary conversion of the binary representation. And then of course, so here in the right case we see the 1, 2, 3, and in the other case we see our strange number, which is the binary representation of our floating point number. And what we can also do with casting and with pointers is if we define a variable, so I think I mentioned that already, as const. Did I? No, I did not. Okay, so let's say if we have a const variable, const int my const is equals 1, 2, 3. Normally we are not allowed to change this variable. Is equals I don't know, 4, 5, 6. The compiler will complain and tell us that this is a const, this cannot change. But if for whatever unjustified reason we would want to change it, we can get an address of this variable, then tell the compiler it's a normal int and not a const int, then dereference that reference and write to it. Of course, one problem with this is that if we would use our const variable to oops, let's do it here, to define the size of an array. So you can do it with a const variable, you cannot do it with a non-const variable, and we are missing the semicolon. So we can only define variables, use variables to define array sizes if the variables are known to not change. If we do this change, this will not be reflected here, or even if we would do this, it would still not be reflected here, because at this point the compiler will just take the value which it knows it would be, put it in here. It will not happen to runtime, it will happen to compile time. So if we would later have a for int e is equals 0, e is lower than my const, then if we would change, and e++, then if we would change my const, then our for loop would start accessing invalid memory. So this is something that should be avoided at any cost, let's say. But there are scenarios where you might want to change a const variable, and if you know that the const variable is not used for loops or other things where it would be taken by value at compile time, then you can do it. Just saying, not that you should do it, but in certain scenarios it might appear it's necessary. Okay, so we will get rid of this since it's a buggy code, just to keep it as a demonstration. And what else would be important to be said about pointers and memory representation? Yes, there's one more thing that I probably should mention. First of all, the way the numbers are represented in memory, which you may already have seen before, if we put a breakpoint here and put here, or let's go to the upper example, to this one. So we wrote here 1, 1, 1, 2, 2, 3, 3, 4, 4, but if we go to the address, where do we get the address? Here we get the address to the variable of the variable. So we have my pointer, we can put it directly here. Then in the computer, in the computer's memory, the order of the bytes within your number, as you see here, in the typical architectures, is in fact reversed. You see, it's not 1 1 2 2 3 3 4 4, but it is 4 4 3 3 2 2 1 1. So, unlike the typical expectation or the typical hexadecimal notation of a number, where the least significant digits are at the end and the most significant ones at the beginning, in the representation how the computer represents those numbers internally, in fact the most significant digits are last and the least significant digits are first. And the reason for this is to help with type conversion and alike. So if we now define a variable of type int again, int my int equals, let's go again with now x 1 2 3 4 5 6 7 8. Okay, not again, we haven't used this, but it's also one of these easy to recognize patterns. And now let's create a pointer to it. So int asterisk ptr1 is equals reference by int1. And then let's do the same, but with a different type. So let's create a short. So it's, as you remember, 16 bits. It's equal, so we can only use 1 2 3 4. Or let's go with A B C D. Okay. Then we can do the same thing. Pointer 2. Points my short. Okay. Wait. Yeah. So first of all, you see the compiler is already complaining that the type is not right. So we should change it to int, to short. Then the compiler will be happy. And here, let's now assume that we have so that a few things we can do. First of all, what we can do is we can just run this and see the two representations in memory of the two numbers, which I already showed before. Always need to go one up. So as you see, it's reversed, and for this one it is also reversed. BA. So the first, like the order within a byte is maintained, but the order between bytes is swapped, which is kind of not intuitive to wrap your head around. If it would be just completely mirrored, that would also kind of be easier to wrap your head around, but it's only swapped on the byte level, not on the bit level. So you didn't see this before, since before we had here always the same doubles. Now you see that it's actually swapped as said on the byte level only. And now let's do some simple conversion. So let's say short my short 2. Actually, we don't need to redefine a variable. Let's just go with the one we have. It just equals int. And if we run it, you see that to short that now, okay, we need to enable hex display, that the short only got these 4 digits. The upper ones have been just dropped. Depending on your compiler configuration, if you do such a thing like here, cast from a larger type to a smaller type, the compiler will throw an error to ensure that you will not that you will notice that you might have a data loss there. In some scenarios, when you know that you will have only smaller numbers, then it's not an issue. But of course, the compiler does not really know what you are intending to do, so it's safer to throw such an error. And now when we go to the memory at the location of R2, of R2 things, you see that so this address, and this address, like the first byte, both of them point to, if we go to the addresses here, will be the last ones here. So you see that here the address points on the 7 8, and the address here also points on 7/8, just that it has a few more instructions. And what we can also see here, when we do the operations here, it's always the same move operation, just that it specifies not a here not a word, but it specifies a not a double word, as it needs to copy a 64-bit value, but it uses a word as it needs just to copy a 16-bit value. So this strange representation helps with copying data, and also with this type of conversions. If both of these values hold a certain number, then like let's say 10 is small enough that it will always fit into any of the machine types, and now it can just copy a simple memory block. It doesn't need to check like which are the highest order bits and then shift them and do some more operations. It is the easiest way how you can implement this type of simple conversions on a hardware level. Hence, this representation has been chosen when designing the CPUs. And of course, it doesn't matter for your external applications how the internal representation in memory really is, unless you want to save whole memory blocks as they are directly to disk and then load them somewhere else. So if you would want to save some memory area and then restore it for some more advanced operations, then you would either need to do it really variable by variable and check for the right encoding, or you would need to know that your application will only be executed on systems which have the same architecture with regard to the integer representation. This sort of representation where we have the most significant bits first, so let's write that maybe quickly down. So we have here our int. So what we can, for example, do as in other demonstration, we can comment this block out. We can define unsigned char, let's say my char, or let's call it say int, doesn't matter, with the size 4, and then what we can do is we can use also pointers and typecasting to copy the integer from here directly into these 4 characters. So we already have the address of this because it's an array, but we need to cast it to int asterisk, and then we need to dereference it. Then we can assign our int to it. So internally this will just do another pair of move operations, and then if we look into our cint, we will see that, as said, it changed the order of our bytes. So effectively this will contain, let's write it here, this will result in cint being equals null x, what was it, 7/8, null x 5/6, null x 3/4, null x 1/2. And this representation, where this order is swapped the way we saw, is called the little endian representation, and it is usually used by many CPUs, ARM CPUs as well. Although with ARM you in fact can, but this with most implementations, you can switch a flag when initializing the CPU to use an other notation. So the other notation would of course be the way as one would expect this intuitively, that it just keeps the order in which the numbers would appear in the hexadecimal representation. This one is called big endian, and as mentioned, you can switch in fact or at least many ARM CPUs to this representation. This is not something you would ever reasonably do within a program. This is something you might do if you are running on a microcontroller and don't use an operating system, just only your application, and for some reasons you see this as being beneficial for your operations. One reason why you might see this beneficial is that you can easier, let's say, parse those numbers if you want to work with them on a character by character basis. Another reason why you might want this is because in most network protocols it is customary to use the big endian notation. I should write big with a big B and not the little endian notation. And if you would, for example, be programming some sort of network appliance like a router or a switch or something that spends most of its time operating on the network protocol level and copying packages around, it might be beneficial if you don't need to convert from those two different representations all the time, because such a conversion, unfortunately, there is no instruction for it. So if you would want to convert from big endian to little endian and vice versa, you would really need to use a temporary variable and then just copy your bytes around. So that would not be let's say the most user-friendly thing. Well, it would just need a lot of operations. It is not one instruction. It is like probably 8 or no, yeah. For this size, it will be probably 8 operations. So it's extremely slower than just one. And of course, if you have 64-bit numbers, then it will be 16 operations, which will be even worse. So there, in such cases, it might be beneficial to have your whole hardware run the network customary big endian notation. So at this point, we will schedule a small homework for you. Nothing too difficult, just the simplest thing I can come up with. Convert. Let's change the name here. Little int. Okay. Which is and convert it to my let's call it my network int. Often so to give you some guidance how to do it, so for example cast int of chars little int quit secondary array. Yeah, why not? A big int is it's not something I would like to call it, because usually you use to call big int some sort of object which can keep integer numbers of arbitrary size, like 128 bits, 256 bits, etc., etc., as used in cryptographic operations and so on. But here, let's call it big int, or let's call it net int. Let's call it network int. That's good. Create a second array. Then the next step would be of network int how do we call that, my network int variable. And as you see here, this is how you can read from an array, and writing to an array is the same. You just write to it. So this code now would overwrite the array variable after over array and after use. In this case, after use, but you can access some. So, for example, if you want to make the last one always being 0, so that would be the third one offset is equal 0. This way you could do it. So I think this homework should be easy enough to be done. Are there any questions at this point? Oops. Or is everything crystal clear? Yes? For this one, it's so simple. Well, okay, why not? Do the same for a 64-bit integer type. Yep. So this matched to the optional option. We might expand on this later, because the next thing we will do now will be the flow control. So as you've already seen, we have taken a look into loops before, because we needed it for the array demo with pointers. But the next thing we'll do now will be flow control. So if you still have some questions to variables, variable representation, etc., please ask now. I also might want to say that the code now is completely uncommented. Before I upload it to Moodle, I will add a lot of commentary, so that you don't need to follow the recording of the lecture and read the code. But the code will become, through the comments, to a large extent self-explanatory. Yeah. So as said, if there are questions, if there are no questions, then we continue now with the flow control part. Okay, seems there are none. Or maybe do you want like a short 10-minute break, since we are supposed to have a break at some point for 15 minutes. We could also make a short 10-minute break now before we start another subject. I think that sounds like a very user-friendly proposition. So, as said, we will make a break now for 5 minutes. We'll continue at let's say 5 past half, so 16:35. And if you have any questions in the meantime, you can ask them at any moment. I just for now turn off my camera and the micro, unless I hear a question, then I will come back. But I will be listening to you all the time if you have any questions in the meantime. So, see you in 10 minutes. No questions? So everything's completely clear. Okay, so create a new project, we call it flow control. And maybe one more thing to say, which I think is quite important. As you see, we have during the past 2 lectures looked onto this assembly code a lot. While it is good to know it and understand it, to get an understanding of C++, it is not something you will need to write during this lecture. So all this assembly stuff, it is good to know, but it is not necessary. You don't need it to make any of your homeworks, etc. So just in case you were worried that it might get far too complicated, it will not. It will be simple enough. Okay, so assuming that everyone is back from the break, let's continue with flow control. So as you have already seen with the loops in the earlier example, if we can change the flow of the execution. So the loop as a parent executes some code, and then it repeats the same code, and it repeats, well, as the name says, in a loop until some break condition occurs, at which point it then again changes the execution flow. Now a loop is a rather complicated in comparison control flow structure. The simplest control flow structure that you can have is a if, and I think we showed some ifs at the very beginning with regard to the logical operations, which you always, well, not always, but often use in ifs. So again, there is an if and there is a condition. So if 1, then blah, or else loop. And the semantic meaning of an if is that if this is a logical true statement, which means if it is not 0, everything that is 0 will end up in the else case. Everything that is not 0, it doesn't need to be 1, it can be anything, as long as it's not 0, will end up in the blah case. So for this, to make the example a bit more helpful, let's define a variable int test is equals 1 to 3, and then so if test is equals 1 to 3, so if this check is true, the blah case will be executed, else the other one. And then also let's make a second variable int test red is equals -1, and then the one case we set it to 1, and in the else case we set it, let's say, to 2. So that's the simplest if structure would be just this. So let's first try out this one and then take a look on the other one. And since we want to have readable code, we will again disable where was it? This one, this thingy. Okay, run. I forgot the breakpoint. Damn it. Was I fast enough? No. Okay, so we have a breakpoint here, and as you see, what now happens is that it loads. Let's quickly disable the names. It loads the value of our variable. As you can see here, the variable is stored at the RBP+4 location, and then it makes and it compares it with the value that we have provided. So 1 to 3 is 7BH, and if this comparison operation will set one of the CPU's status flags, depending on whether it is true or not true. And then this JNA instruction is so JNA stands in this case for jump if non-equal. In ARM, the instructions are called slightly different, so it's not a one-to-one. You cannot take the code or anything that, well, not anything. It is difficult to convert x86 assembler code to ARM code. So basically you just need to write it from scratch again. It is to that extent not compatible. But the C code that you write, which you will be writing in this lecture, the compiler just translates it to whatever appropriate assembler representation or machine code representation is required. So you don't need to know all those individual opcodes. It's just helpful to at least know some of them in case you are debugging something where you don't have the source code too. So JNIM means jump if non-equal. So in this case, if it would not be equal, then it would jump to this address, which you see is here, which is past the loop. So if this is equals, then this doesn't do anything, as in this particular case. So let's step through it, make the comparison. You see that here the instruction pointer changed, since we are now pointing to the next instruction here, and we see that the different CPU flags have changed since the CMP operation was executed. The CMP operation does not only compare whether things are equal or not, it will also give you flags set whether it is greater or less than. So all those different operations usually can be executed with the CMP operation and then with the appropriate conditional jump instruction. Okay, so we are here, but since it is conditional and the condition is not met, the instruction doesn't do anything. It just advances the instruction pointer to the next instruction. And here we are just assigning 1 to the memory where our test return variable lives. And we are done with the if. So first thing we can do is we can enable our else case and rerun the code. You will see that this will add a unconditional jump. And that's it. So the begin is the same, just that our jump target here is here the instruction, the first instruction in our else case, instead of being the first instruction after our scope. And then what it added here after we have assigned the value, it added here a unconditional jump to the address to the next address after our code block. So to make this even more clear, we can maybe here return our return instruction, our return variable, I mean. So here you see that the one jump, where is it, goes here to the next instruction after our loop. Sorry, after our if. We can of course test this also with the, let's say, greater test case. So in this case it changed to jump less or equal, less, greater equal will be yet again a different conditional check, jump less. So since it kind of has a built-in negation, what it does, in the before case where we were checking if it's larger, then it was actually using the jump if less or equal, and here if we are checking whether it's larger or equal, it just have a jump if less, or rather jump in case of it is being less. And as said, the compare is always the same one. In different architectures that might be different, and in fact there is also like the test opcode which actually tests if something is 0 or not on x86, but it's I'm actually not sure if the compiler will use it in this case. Let's see if it will. No, it's not. It's just comparing with 0, but as said, this is not optimized code, so it might look different if we would have to have enabled all the different optimizations. What we can also of course do here is, let's say again this is equals 1 to 3. We could also have non-equal, then of course it would again change the instruction, but I guess you are getting the point, so we don't need to spend too much time iterating through all the different options. But an interesting thing you can also do with ifs is a so-called else if, and this basically works like this. If this is true, it does this. If this is not true, it does else. And this is technically equivalent to writing a code block like this. It is just more inlined and looks nicer if you write it this way. Then you have another else where you can test var as equals 456, or let's say it's larger 456. And then we can of course use the logical operators which we already learned earlier. So or it is equals, let's say it's smaller than 789. In this case we will set the variable to 3. It's up to us what we do in the if so. It just allows us for a certain level of complexity. And when I mentioned earlier that when you would not use any arrays, you could in principle access multiple variables, you could have such a huge amount of ifs, but that would be highly unpractical code, so obviously no one would ever do it. But in certain scenarios where you have two variables, for example, only two, and a more complex access situation, which one do you want to access, you can use such a if. So in this case we write different values to the same variable, but you could also write the same variable to different the same value to different variables, or do other things. You can put any code that you can put in a function also in an if. So you can also define here a local variable int test x is equals 1, and then do something like this, or is equals 0 plus plus, whatever you want. You can put another if in there, as we already said. You can put a loop in there. Your imagination is the limit. And what we will also learn later, once we start with the C++ part of the course, is that you can define operators for variables which represent objects. So you could have very complex mechanisms which would then be implemented within your if. And another thing what you also can do is you can have a function call within an if. Basically, you can have a function call in any equation, and of course, since you can put equations into ifs, you can also put a function call into if. But function calls is something for later, since it's again a bit more of a complex subject. But one thing you can do with ifs, or rather, what you can do with simple data types, which you cannot use, which you cannot do with more complex non-machine types, is you can use a switch statement, which is some sort of a very simplified sort of if condition set of if conditions. So for the switch you provide the variable name, and then you provide in cases values for which you want to test whether the variable has them or has them not. It doesn't support greater or smaller or anything, or unequals. It only supports comparing with a set of known values, and it also requires us to break this case statement. So we need to write break. If you would not write the break, the code execution would just pass this and then go to the next case. Obviously you see here the compiler is complaining that it's the same value, so we change it. So if you would forget the break, then you would always end up with 2, whether the variable is 1, 2, 3 or 4, 5, 6. If you have the break, then it will break here and then jump to where the switch statement ends. You can specify the variables in any order, and there is one special else case which is called default. This case will be simply triggered when none of the other options provided is true. And in principle you can also should also put a break in your default case, because you can have the order of the cases is arbitrary to you. So you can have something like default or which, how much were we? 6, 7, 7, 8, 9. Then we make it 3. So for example, if you would do this, that is kind of pointless, because the default case will catch this case anyways. But you could do it if you would want to. You could, of course, or if you would want in the default case to do the same thing as in the 4, 5, 6 case, you could do this, etc. What you can in fact also do is you can make the break conditional. So you can say if it doesn't really make sense in the context of this particular example, but if you would have another variable int test tmp is equals null. So if you are in the 1 to 3 case, you could test if this is not null, then break, or if it is null, then don't break and go to the next case. And this looks obviously like a great opportunity to forget it and make some mistakes, which it is, but it is actually quite useful, because you might have situations where you want to do a certain amount of execute a certain amount of code, and only in a special additional case do also something else. So in this case, you might to use such a case structure and really want to fall through one case into the other case for something to be executed. It is not very common, and since it is very error prone, it is recommended to instead use just ifs when you can, and when it's reasonable. But for example, if you would want to convert a lot of values into other values, so let's say we can define if a is a and b is b and so on. B is b, and I mean this particular example can be done much easier. But D, E, F. But for the sake of example, let's just go with the A, B, C, D, E, F. Let's go with this, and then let's say we have our int test1 is equals 0x a. So, and we want to have a result. So so it's supposed to be a test2 is equals 0, result of 0, and then we want to get the character value. So we make a switch from our first value, then we make a case, and we assign this is equals a Strichpunkt break, small b Strichpunkt case 0x a Doppelpunkt a. And then we just 1 2 3 4 5 6 B C D E F. Okay, I have to one too much. B C D E F, and voila, you have a code which is very compact, converts between one set and another set of values. To convert the other way, you would need to write another code block which do the opposite. But this is, for example, a use case where using switches is the most expedient solution. And it's also not so easy to forget a break if the code is so symmetric as in this particular case. So this much to cases. Or maybe one more thing that should be mentioned with regard to them is let's go here. If you would want to have a variable int x is equals 1, the compiler will not allow you to do that, because you don't have a separate scope. So if we build this, it complains here that initialization of x is skipped by case label. But you can of course put your code block into a scope, and then it's fine. If you do this, oops, I misclicked. It will just compile, because what happens basically is that the variable gets initialized here when we get into this case, but we are still in the same scope when we get to default and to this case, so it doesn't know where the variable should really stop existing. But if you give it a case, then a scope, then it is fine again. So this much to that. The loops we already have taken a look at earlier, but now let's do it in detail. So int my counter is equals 0 for int e gleich 0 ist kleiner my counter schönig e plus plus, then schönig e plus plus. And then let's do the simplest thing we can, just increment our counter. So we'll end up with the counter being 10 once we're done. So we put a breakpoint maybe here and run it. Zack. We already had a breakpoint, so let's unbreak this point and then go to the other breakpoint. Okay, so here we have, of course, our my counter initialized. It's a single opcode. Then we proceed with our for loop. So here you see first we have here again the initialization of our I variable. Maybe I should enable the names. As you see here again, for the loop counter, it for some reason does not show us I. For the other one it does, but we can use keep this because it at least makes for a more readable code. It just also here removes the useless zero, so it's a bit nicer. And it introduces some dummy labels, which is also nice. We will take a look into labels in a short while. So as said, here we have our initialization of the loop counter, then it jumps to a code portion which compares here the execution. So the flow is this: first we make this, then we compare whether we are allowed to even execute the first iteration of the loop. So if we would initialize this with 10, then the loop would never do anything. And of course, if you write things by hand, that's a different story. But if you would initialize your start variable with some other variable that did something, for example, as a part of some word processing or log file processing, etc., you might have often situations where you really don't even want to execute the first iteration of a loop in certain scenarios. So that's why this work this way and makes this check each time, even the first time. So we have this compare, then we have a jump if greater or equal. So the jump would terminate the loop. So we see here that the address where it wants to jump to is where is it? Okay, I'll turn this off. Yeah, is here after our loop. I don't know why I didn't show this with this display. I disable the name display because the address highlighting works better if it's off. But since the condition is not yet met, so or rather since the condition is still met, so we are still iterating. So this evaluates to true. It will then execute here our incrementation operation. So it gets the value, it increments it, and then it saves it back to the memory. So apparently the increment opcode itself cannot be executed on a memory address. Okay, so we do our thing, and then we have here the jump instruction, which will bring us to the part which we here with this unconditional jump jumped around. This move and in can't move again. So click. You see here, what we do is we get now the value of I, we increment the value of I, and then we save the new value to the memory location of I. And once we are done with this, so zack, 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 we can do the comparison. So we compare the I variable with 0 and then, sorry, with 10. 0a is 10. And then depending on what happens here, we continue. So at some point this jump will be executed, at which point we will exit the loop. And what you can do in such a loop is you can control the loop's execution by using two types of keywords. So you can have the continue keyword. Continue will abort whatever the loop does right now and jump to the next iteration. So if you have some additional code further down the loop which you don't want to execute, you can skip it by continue and go to the next iteration of the loop. And you can have break, which we already saw here in the switch statement, which will just break out of the loop. These two are quite useful keywords. One major limitation of both is that they always only apply to the loop you are in right now. Or if you would have a switch within a loop, then from the switch you could use the continue, because continue has no meaning in the context of the switch, but the break within the switch is always valid only for the switch. So within a switch in a loop you would not have a way to prematurely break out of the loop. So we can construct some test cases here. Okay, let's first maybe add a variable int my test is equals null. Okay, so if my test plus plus is equals no, let's do it differently. Yeah, we need it. My test. We don't need my test. We can just use the I variable. That is good enough. So let's say if I is equals 3. So during the third iteration, that needs to be before the code. We want to continue. So during the third iteration of the loop, which has 10 iterations, we want not to execute this code at all. And for good measure, we will also add yeah, if I is 9, then we want to break completely. Break. So if we are at the end of the loop anyways, we would want to terminate before we do the last execution. Normally, once we are done, it would do the incrementation and then break again. So we can take a look at how this code works on the machine level. And we will not step through everything because it would take too much time to get to this. We just see that here we have our comparison. And then we have conditional jumps in case of the continue. It is a jump to the address here where the next loop iteration is executed, and in case of break, we are jumping to the address after the loop where the next opcode is. So this much to this, and now to the other types of loops that you can use in C++. So we reset. Yes? 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 In this particular position, it is meaningless because you are not evaluating the result of the operation. So this is equivalent to this. Where it would not be equivalent would be in the following case. So, well, this is a simple thingy, but if you would so if you would want the operation to be always done on the I, so we would have, for example, I++ here, then it would work like this. We start out with 0. This does the incrementation. So now I is already 1, but it checks if I was, so like the old value of I, which is now cached in a register, is less than 10. So this loop will execute like this still 10 times, but it will give you I values. So here we have I is equals 0 through 9. In the instance I becomes 10, the loop is not longer executed. So after the loop execution, I is equals 10. We should comment this out, since then of course the I would not longer be 10 but 9. But in the normal case, in this case you get 0 through 9, and when it is 10, then it is not executed inside and it terminates. In this case, you would get I's within your loop body. So maybe I should move this here just for clarity. Within the loop body, you would get I's which are 1 through 10. And if you would do ++I, then you would I's which go 1 through 9, because then the loop would abort one iteration earlier, because it would not evaluate the old value of I, but already the new, already incremented value of I. Yes. Good. So the next loop type is a while loop, and it's pretty much just a cut down for loop. So let's say while counter is kleiner 10, counter ++. So the while loop just has a condition and nothing else, and functionally it is just equivalent to a for loop with nothing in the first and last place. So with no initialization and no execution afterwards. And then we need to have some code here, like for example the incrementation. We can remove this breakpoint, add there breakpoint, run the code to see how it looks. It will be very similar, just a bit simpler in the structure internally. So as we see here, first we reset our variable, then here we do the comparison, we do the conditional jump, which we will do on the last iteration, since for now it's not for now it's still true. Then we do our operation, and then we just jump to the beginning, and this repeats until we jump out. So the while loop is really like the simplest sort of loop that you can have. Of course, you can use the plus plus operators within your so let's say int e is equals null. We reset this to 0 again. So you could also make something like I plus plus is kleiner 10, and then here counter plus plus. That would also give you that would be pretty much just this case, and 10 iterations. Yeah, and the next type of loop that there can be is a bit more fringe. It's not used so often. It's a do while, and this is the only loop type where the evaluation of the condition is done after the first execution of the loop has been executed, and it needs here to be terminated with a semicolon, obviously. So we add some code. We want to reset this as well. Put a breakpoint here, and if we run this code now, we will see that here we just set 0, and then we just proceed with our first execution of the loop body, and only then we check and we compare and then check whether we should execute again or jump to the or just so in it is like it has a different structure, since we will always jump at the comparison as long as this is true to repeat the loop, instead of jumping out of the loop, what would be the case in the other loop. And also you save on operations, since you don't need the jump and repeat, the explicit unconditional jump and to the repeat as you have here. So as you see, the amount of operations you require for a do while loop is reduced, but you are losing the ability to make a decision before you enter the loop. You will always enter it, which in certain scenarios is what you want anyway. So it's good to know those different loop types, and hence always know which loop to use when. And the last thing with regard to loops and so on, which should be mentioned, is how to break out of multiple loops. So let's say we have 2 infinite loops. So an infinite loop is just a loop without a condition. You can do it as a for loop. You cannot make an infinite loop from a while loop this way. You can of course always just write while 1 and that will also give you an infinite loop. But the recommended way is to use a for without anything anywhere, as this saves on the most instructions. Although nowadays, of course, it's so expected that the optimizations of the compiler, if you write while 1 or if 1, will just remove the code, at least in the release build. So how would we go about breaking out of those 2 loops at the same time? So of course you can break out the first one like this, but how do we break out of the next one? One option would of course be to have, like, let's say this plus plus, and if this is more than 10, then break, and then have the same condition again here. So we will do the loop, then we see the condition, okay, we break, then we are in the other loop, we see the condition, we break. This is a doable strategy, but it needs you to duplicate code, which often might not be what you might want. So what you can do is you can specify a label breakout. A label is basically just a name followed by a double point somewhere at the beginning of the line in your code, and then you can use the goto instruction, go to breakout. And then the goto instruction pretty much just implements an unconditional JMP instruction. So when it is invoked, it will just redirect the execution flow to your breakout. So when we can a breakpoint here. Do we have other breakpoints? No, and run the code. And as you see, our infinite loops are quite simple because they don't have pretty much anything except the jumps to repeat them. And here in our breakout, here we have the jump to after the last instruction. Or of course, if the breakout, why did it? Interesting. For some reason, it copied the instruction. This is not necessarily, you only need one of them. I don't know why the compiler did that, but I assume if you would run it in a optimized build, it would not duplicate unnecessary instructions. Yeah, because it's still a jump to the same address. This is just strange. But this is how you can jump out of two loops, or if you would want to break a loop from within a switch, then this would also work this way. There are at this point a few things to keep in mind about this go-to instruction. So we don't need to use it in a loop. We can use it anywhere. So we can have just some code, and for example, we could put here go to breakout, or if counter is if counter is not null, then go to breakout, because we already did something with it. But if it is null, then do the thing. So or we can also give it another name. Go to skip loop. Then we just need to have another label, skip loop. One thing that is a bit tricky with those go to instructions is that if you would here define like int test x is like 0, then you see the go-to gets underlined, and it complains that that the transfer control bypasses initialization of test x, because here after the loop you could have if test x is equals 1, then return 1, I don't know, something like that. So we would the execution flow would jump from here to here, not initialize the memory for test x, but here it tries to reference it. So this would be an obvious bug, and hence the compiler does not allow you to do that. And there is a couple more similar issues with using gotos. So for example, if you would want to fix this issue, you would need to, what could you do? Well, if you don't want to do this and just want to have your goto work, then you can put this in the scope, because then the compiler knows, aha, here we have this test x, but here when the scope ends, this test x stops existing. So when we skip around the whole thing, it is safe to do. So I would not recommend using gotos if it can be avoided, as it provides for a usually quite unreadable code. Of course, in very simple examples like here, it is fine to use it. But if you would have much more complicated code, longer functions, a few dozens or hundreds of lines, and then you would be using goto to jump from one place to another and do things in a hard to trace or track mentally order, then if anyone tries to read your code, or if you try to read your code after a few years or months, then it's just not a pleasant experience. So wherever possible, you should use loops and ifs, and just use gotos if it really actually improves the readability of the code by, as in this example, avoiding replicating the code, or also avoids unnecessary opportunity for bugs. So a code like this, which on multiple places compares a variable to a constant value, is prone to, okay, I will need to change this to 11, for example, and then you forget to change it to one of the places, and then your code behaves erratically. So of course you could have a variable where you write 10 to, or you could replace 10 with a preprocessor definition. So of course there are ways to make even redundant code readable and safe, but especially for breaking double loops, it is really a better idea to just use the goto instruction, since this really saves you on headache further down the line. Um, okay, one more thing we could take a look on is, for example, if you would want to write a loop without actually using a for or while or do while. So if we only have ifs and goto at our disposal, we could write a loop ourselves using goto. So you can have int my sorry, the counter value we have, so we just reset my counter is equal 0. Yes. Then we have I think as well, I is equal 0. Then we have our next. Then we have our condition. If I is 10, then go to done. Now we have our function body, my counter plus plus. The label does not exist yet. Then I plus plus. Then go to next. And done. Oops. This is how one would interpret the loop, the normal for loop, intuitively, let's say. But as you would, when you would compare this with actually how our for loop is really implemented by the compiler, you will see that the actual implementation is very slightly different, because as we see, after here, after the code, we only have a go to next. Yeah, and then here next does the incrementation. Then we have the check, and then we have our code. So here we would want to, after the we need a label here, done. So we still need that double point. Righto, and here we need something to like skip. I use skip. Okay, I use skip loop. So let's call this skip, and here we have a go to skip. Let's see, is this the same thing? So we do our initialization code, then we skip the incrementation, then we do the test, which allows us to go after it, then we do our code look, and then we go to the next label, which does the incrementation, does the test, and then it will, yeah. So this is actually how a normal for loop really step by step executes in the processor in machine code. Okay, are there any questions at this point? Like with the other example, I will add much more comments before I upload it to Moodle, so don't worry that today we only have written code with no comments. I will add them in shortly. Yes? Mm-hmm. Yes? The simple answer is you cannot. There are certain scenarios when you would be using namespaces where you could try to some extent reusing names, but within one function, if you use a different if you reuse a variable name in the scope, then there is no way to access the variable from the previous scope. If you really needed it, then I mean you can of course use a reference. So let's make an example. Let's go back to our pointer example. And let's say so int my int x is equals 1. Then we have our scope in which we access which we have a short. My int x is equals 1. Okay, let's say it's equals 2. And what you could do, if you know that you're entering the namespace and that if you know that you need to use this variable, then you could say, for example, int reference my outer x1. So before you redefine it, you still can access it. Only after you define it, you cannot. So now you have your outer int x, and then you can here do something. Then you can have my outer is equals, let's say this, and it will effectively work. It will change the value of our outer my int to 2. So it's a trick. It's not something you can do within the language by... It's like with breaking out of loops. You cannot break out of 2 loops using break and telling break that it should affect the outer loop. But you can break out of 2 loops by exploiting the goto mechanism. So similarly here, when you are in a scope and you know that you reuse a variable, then you can exploit the reference mechanism to create a abstracted pointer on your external variable, and then whatever you do to your reference through the pointer mechanism will affect your outer variable. Yes, let's say, oops, if this equals 1, that should be perfectly fine. And then we will end up with int being 2 after this particular code. Okay, any other questions? No other questions? Okay, if there are no more questions, and since we were slightly over time the last time, I think we can finish today 2 minutes early. Since we only had a 10 minutes break, we should have ended 5 minutes early anyway, so everything is fine. We will see each other next time. I will upload the homework here, this one, to Moodle. Why did I don't think I invented any more homework in the other example. No, I did not. Good. Yeah. So you will have your homework. I have seen that only 2 people have submitted the homework from the last week now. So is it difficult? Do you have any issues or questions about the last homework? Or maybe the current more in-depth dive into pointers will help you anyways. Okay, yeah, if there is nothing else, then I'll end the stream for now. We will see each other next week. Have a nice weekend. Bye bye.